Excuse me, sir. Can't hear your voice. Excuse me, sir.
Yeah. Is it audible now?
Yeah, audible.
All right. So, so I was trying to standardize the data, or normalize the data. So what for normalizing the data, what you need is you need the value which you want to normalize, and then you need the mean of data, which is $11, right? So I will say $A, and $11, right? And then we need the standard deviation of the data. The standard deviation of the data was $A and $14. This works. Okay, fine. Then I will drag this whole data here. So this calculates this normalized data for every individual value, individual X value. Now we can see here, this is the mean, right? This is the mean of this whole normalized value, which is 0, right? You can see this is a number is minus 1.1 raised power minus 16, that's almost 0, right? So this is a 0 value. We got a value of 0 for our normalized data, and we got a standard deviation of 1 for this whole data, right? Okay, so some of you may be confused why we have a minus 1.7. This is actually 0. This is equal to 0. And if you're confused with this, I can directly use the value of 4.44, and here I can use the value of what we had 2.66, right? And then if I calculate it, see, this becomes 0.001. That's almost 0, and standard deviation of 1, right? So every normalized data will have a standard deviation of 0 and sorry, a standard deviation of 1 and a mean. Okay, so let me switch back to where and let's get a tab. So what we know now is we can calculate the data, and we can calculate the standard deviation, we can calculate the variance of the data or the standard deviation. Now, some of you may be confused. What's the difference between standard deviation and the variance, right? Right. This may be a confusion with some of you. Now, standard deviation and variance has no difference. It's just a square of it, right? If you calculate standard deviation, if you put a square over it, you will get a variance. Or if you have variance, you put an under root or square root of the variance is always standard deviation. So I don't see any difference between the two. Now, why we have two? There are so many, reasons. Okay. Okay. So,
Sir, can you please repeat? Some disturbance was there.
all right. So we measure variance using standard deviation. We measure variance or using variance as well. So there's no difference between variance and standard deviation as such. But sometimes we use standard deviation, sometimes we use variance. They have an equation or they have a relationship between the two, is that standard deviation is the under root of the variance, or variance is the square of the standard deviation, right? Okay, so but people prefer to use standard deviation. And just a minute, let me move all this. Okay. People prefer to use variance over standard deviations at times because we have some other mathematical reasons for that, which the scope of this course is not to move into that dimension, but we should know as a data scientist or a problem solver in any scientific field, we should know that using standard deviation and variance does not bring any much difference to your predictions and other. Okay. So then we found empirical rules, and okay. Now we will have another dimension of understanding data before we move further. Is we have data is sometimes related to each other. Like we people have a relationship. We have a brother and a father and a family and other things. So has data. Data may be related to each other, right? We may have a relationship among the data. Now, data from a single source or a similar process, sometimes from a single process or a similar kind of process, is inherently related. Yes, it is. And knowing one feature may help us predict another feature. If we know that one feature of the data, we can predict another feature of that process or data. But before making any predictions, we must understand what's the relationship between different features of the data. Like say, if we have health card data, we have the data from the hospital, and if we can find a relationship between obesity and your per capita income or your salary, if you have a data related to your salary and obesity, and if we can find a relationship between obesity and your salary, then we can make predictions and we can tell people, see, if you have more salary, you may be more obese in future, right? or if you have a less salary, you can be less of it, kind of thing, you know. Or sometimes we find a relationship between smoking and deaths, right? So we can tell people, see, if you can smoke, if you smoke more, there's a high probability that you may die earlier. So these kind of relationship helps us to make predictions or to tell more about your data, right? More than what the characteristics of your data is. Now, before we can make relationships and we can make predictions, we need to see how we can first calculate this relationship. Now, how we can calculate relationship among different features of data is, for example, we have attribute X and we have attribute Y, and we can say that X and Y are related, or they have a correlation among the two. Is that if X has some predictive power on Y, predictive power means if using X we can make some predictions about Y, then we say X is correlated to Y, right? But not necessarily we have a reverse case that Y is able to predict X. We have different circumstances for that. Okay, we use correlation coefficient to measure the intensity of this relationship. So, for example, we have different intensities of relationship for humans as well. So we have different intensity of relationship among and different kind of features or data variables as well. So it's not like someone is related, but what kind of relationship they have is important, right? So in order to assess or measure the relationship among two different features, for example, features like smoking and death, right? For example, features between the relationship between the uh, obesity and your annual income or your monthly income. If you want to find the relationship between the two, you need to use a term or a way out that's called correlation coefficient. Right? Now, let's not be afraid or scary about these correlation coefficients and how we calculate it. Excel gives you just in a jiffy or just in a one click, you can calculate the correlation among the two different variables or features. Uh, let's go a bit further in this correlation. Correlation, some of you which may be knowing or which are about to start or launch into machine learning or artificial intelligence or your own problem solving, you may find a term called Pearson's coefficient, which is the same, but is correlation coefficient. So don't get confused. This is the same as Pearson's coefficient, and it helps you signify the relationship among the features of your concern. Okay, we denote it by R, small r. Okay, and the value which a coefficient takes on is in the range of -1 to +1, right? So we can have a coefficient having a value between -1 to +1 to 0, right? So the value of this R, correlation coefficient, or it's simply a variable, and this variable tells you something more about the correlation. It does not only tell you that the two are related, it tells you something more about it. Like if the value of the R is greater than 0, we say that the relationship among the variables, let's say this is an x-axis and this is a y-axis, and if the value of the R is greater than 0, we say this is a positive correlation, right? There are types of correlations. There may be a positive correlation. Positive correlation means the increase in one variable increases the another variable. For example, the more you smoke, the more is the probability that you will die, soon, right? So there we have a positive correlation between smoking and the deaths, because increase in let's say increase in the number of smokes per day will increase the probability of your dying sooner, right? So there is a positive correlation. So both increase in one increases the another way, right? Then we have another kind of relationship or correlation between the data. One feature, increase in one feature may be decreasing the another feature, right? For example, we may have another kind of correlation, negative correlation example we may take is, for example, the more you study, the more you prepare yourself for this course or some other topic is the less likely you may fail in the final test, right? So increase in intensity or increase in the number of hours you study will decrease the probability that you will fail. So we have a negative correlation between increase in number of hours and the probability of failing, right? So that's a kind of a negative correlation. So if the value of R is less than 0, we say the relationship is negative. Sometimes we don't have a relationship among the two variables. That's quite okay. So if the value of R is 0 or just around 0, right, we say there's no correlation between the two things. There's a famous example or a famous talk about a presidential election in United States, and where they tried to find a relationship between a football match and the choice of president for the United States, and they terribly went wrong in their predictions. So sometimes we don't have a relationship among the two, and it's okay, right? It's quite okay, and we should accept it, and we call that zero correlation. So correlation may be positive, increase in one, increase another, and correlation may be negative, increase in one, decrease another, or decrease in one, increases another thing, right? And we may have no correlation among them, right? So let's take examples of some correlation before we do it in we will do it in Microsoft Excel, but let's get more about it. Are taller people more likely to remain lean? Now let's go through it. The observed correlation between the height and your basic mass index BMI is R is equal to 0.7111, right? What is the ratio we can say? So this is actually 0.7. So the height is indeed negatively correlated with, so a person with more height or a taller person will have a lesser weight, lesser BMI, right? So there is a correlation, and it seems to be a very strong correlation, but this is positive in nature, right? So sorry, this is a negative correlation, right? Okay, this should have been negative. Now, does financial status affect the health? The observed correlation between the household income and the prevalence of a coronary artery disease is minus 0. This is not a colon, this is dot. So this is minus 0.717. So yes, the wealthier you are, the lower your risk of having a heart attack, right? So we found a correlation between household income and the coronary diseases. Now, this is another example of correlation. Now, sometimes some of us will be scary about this. Does smoking affect your health? Yes. The observed correlation between a group's propensity to smoke and their mortality rate is 0.716, right? So there's a high correlation that the more you smoke, so increase in smoke, or the intensity of smoke, or the number of smokes you get per day, has a strong correlation between with the mortality, with the death. So this is 0.71. That's quite high, And when we take more examples, and for this, someone, if you want to see the source of this correlation, you can find this data on this URL, which I have mentioned, right? So how does this going to help us? Why we do this correlation kind of thing? Why we calculate these correlations? Once we find a relationship among the two features, we can use this relationship to make predictions, and we really can. So this is the first step towards inference. This is the first step towards the baby step towards making predictions, right? You find a correlation between the two. You can, if you find a correlation between the height and the weight, then you can make predictions, right? You can take on if you have only height, you can make some predictions of what kind of weight this person is going to, right? So correlation is ultimately used in predictions, right? Before we move to the Excel, there's a small portion, and which is very important. You must note it in your notebook that correlation does not imply causation. What is it? Causation means something which is implied by, right? Correlation means that there's a relationship or a pattern between two different variables, but it does not tell us the nature of the relationship between them. Nature of the relationship means what? It can tell you whether it's positive correlation or the negative, but nature does not tell you that. It does not tell you about the nature means that it does not imply things. It does not imply things. If we take an example, is like this. For example, smoking leads to more deaths, right? Smoking leads to more death, but more deaths does not lead to smoking, right? There's not a reverse case, right? It's not a causation. Just because you have more death does not mean in a society you have more deaths does not mean people here smoke more. There are so many other variables, right? So sometimes you should be very cautious about understanding the correlations, right? You can have a correlation among two different features, and that can be incidental, right? That can be incidental in nature, but in reality, it does not imply anything. So you should be very cautious when you try to calculate the correlation among two features. You should always have some similarity, or there should be some kind of relationship, real world relationship among the two variables. Then you should use correlation coefficients, right? And on the other hand, the causation implies that beyond there's a relationship between the two events, one event causes another event to happen, right? So sometimes you have a correlation. For example, causation is you smoke more, yeah, you will die earlier. This is a causation. Because of this one event, some other event is going to happen, right? You study more, you will get good grades, right? This is a causation effect. One thing implements another thing, right? Or one thing affects another thing. Because of the one event, next is going to come very soon, or next is going to follow. That's causation. One thing will lead you to another. That's called causation. And correlation, on the other hand, is there's a relationship between the data. And just to summarize it, correlation is about data and causation is about events, right? But you should be very cautious whenever you apply correlation and then whenever you take, implications from that. Okay, so let's break and let's move straight to Excel and perform some um, computation, and let's find some correlation among the data, right? For example, how we calculate correlation coefficients in data. Let's do it. For example, we have some grades. Let's say we have some grades, and what we are going to do is we want to find a correlation of grades with the hours of study, right? So hours of study. Okay. For example, someone got grade 2, someone got 4, someone got 6, 5, 2, 8, 5, out of 10. Okay, so 9, and someone got 7, someone got 4, 10. Okay, now hours of study, this person studied for 1 hour, this person studied for 3 hours, this studied for 6 hours, 3 hours, and 7 hours, and 3 hours, and 7. I'm just fabricating the data, okay? Just to make you understand. Okay, this person used 5 hours, and this person used 3 hours of study. Okay, this is the hours of study for a test, and these are the grades they got, right? So let's try to find a correlation between the these two different sets of data. And okay, before making any correlation, you must know that before doing anything, we must normalize these data, right? So we must normalize before finding any correlation. Okay. So let's normalize this, and we know how to normalize. So we call it GN. So grades normalize, and we call it HN, hours normalize, right? So we know how to normalize. Let's normalize the grades. We standardize. Okay. No. Before normalizing, we should have the mean of the data. Okay. Let's take the average. So we take average of this data. Right. Okay. And we also need to do standard deviation of this data. So we will write standard deviation with the P for population, right? So we will calculate the standard deviation of this data. Okay. So because this is a this data may be from two different sources, or this data belongs to two different sets. So we should always standardize data before we apply any correlation and any kind of operations. So same we will do here. We will find the mean of this data. right? Average. So let's take an average of this data. Okay. Fine, we got the average. Then we will take the standard deviation of this data, right? This the standard deviation of data. Okay, fine. We got the average grades 5.111 and standard deviation with the standard deviation of 2.333. And here we have hours. So on average, a person has studied for 4.22 hours and with the standard deviation of 1.986. So whenever you look at standard deviation, you should know the spread, right? This is how spread the data is, how you know spread or how the data is deviated from the mean. Now so we got it. So let's normalize the data. So I told you that we have to use standardize function, and this is the grade, and the mean we have is dollar. Why I use dollar? We use a constant, right? Dollar a, dollar 11. So this is highlighted one, right? And then we want to have the standard deviation of this data. So we have dollar a. Well, tells you about standard deviation, right? So this is the normalized data. Right? So this is normalized data for this. Now, is this normalized? Really normalized? Let's, if we get an average of the data, it should be 0, right? Any normalized data, then an average of 0. Right? See, this is 0, right? And if you check the standard deviation of this data, right? Just normalize it, right? It should be 1. Okay. This is 1, right? Don't look at this big number. This is actually e raised for minus 16. So this 10 raised for minus 16. This is almost equal, right? Okay. Then let's normalize this hours. To normalize this hours, what we do is equal to, then we will do standardize. And then we have this is the value, then a, no, dollar b, okay, dollar b, and dollar 11. Right? This highlighted one tells you about the mean of this data, and the standard deviation is dollar a, and dollar this one, not a, sorry, this is b. This calculates standardized value. So I'm just dragging so that I can put it for each value, right? So let's see if the mean of this data is 0, right? Average, right? The average is must be 0. So this is 0, okay. And this should be 1 standard deviation of this whole data. And this is very important. Every time you take every time you want to perform or understand a correlation among 2 different sets of data or perform any operation on the data, you must always convert the data first in a normalized form. Like this is a normalized form data, and this is the normalized form for hours, right? Once you get the normalized form for both of them, then what we need to do is we need to calculate the standard deviation of this. Sorry, we need to calculate correlation for these 2 kind of data. So if you want to calculate the correlation, you can manually do it, but the Excel provides you many ways. So one of them is CORR, correl. This is the function which performs correlation. Now it needs 1 set of data, that is this. This is the first array, right? And the second set of data, this is this, right? Okay, and I perform. So this is the correlation value. Sometimes people do not use this correlation. They use another way that's called Pearson. Pearson also gives you the same thing. Okay. This also gives you the same thing. You can use the Pearson. So this is also known as Pearson's. And if you use another equation, this is it, right? It's the same. You either use Pearson or this. This is the correlation. This is the relationship between correlation, right? This is the relationship between grades and hours of study, right? So you can say this is a positive value. This is 0.888, 0.88211. So this is a positive value. So increase in number of hours is going to increase your grades, right? Increase in number of hours is going to increase the grades. So we can find this is a positive correlation. Right. So then you can use this R, this value 0.88 to make predictions for those values where you do not. For example, someone tells you I study. So see, there's 1, 3, 6, 5, and we don't have a value of 4. Someone says I study for 4 hours. Can you tell me how much grades? Can you predict my grades? Yes, you can predict his grades using this correlation coefficient. This value 0.88, right? So you can use it. Or but one very important caution before we conclude is you should always use this correlation coefficient for predictions with a caution. What kind of caution is that? Is you should, for example, this correlation is for a minimum value of hours is 1 with the maximum value of hours is 7. You should never use correlation to make predictions for number of hours, 8 hours, 10 hours, beyond that upper limit. You should not go beyond that upper limit, right? So this is a correlation defined for a value with a minimum of hours 1 with the maximum of hours 7. So you should always predict between 1 and 7. Or if you take on grades, so you should make you can also make predictions using grades to see how many hours this person has studied. So the minimum hours is 2, sorry, minimum grades is 2 and the maximum grades is 9. So you should not make predictions about the 10 grades, 11 grades, or make predictions for the 1 grade, because whatever correlation coefficient you have calculated, there is a limit on it. So the minimum value and the maximum value should always be maintained. You should not make any prediction beyond those minimum and maximum values. That's a very important thing. So I hope this recording will be, we're going to upload it today. And if you have any sort of feedback, we will take it as a